Chemists study how matter is composed and its properties and how they change. Matter exists in three states as a solid, liquid, and a gas. Their behaviors are determined by the arrangement of their particles. Substances have unique physical properties, characteristics of the substance itself, and chemical properties. Characteristics of the substance when it interacts with other substances, and changes. Changes in matter can be either physical or chemical. Changes by heating can be reversed by cooling, but not vice versa. Submicroscopic changes lead to macroscopic changes, and matter changes are due to its energy. An object's potential energy is due to its position, while its kinetic energy is determined by its motion. Energy changes form but is always conserved. And the science behind how alchemy, medicine, and technology place little emphasis on objective experiments and focus on mythical explanations and practical experience. However, they still had a certain contribution to the overall apparatus and methods used in chemistry.
Okay, so I'm going to talk about chapter 2.7 about compounds, which the majority of elements occur in a compound with different elements. And although there are some elements that occur free in nature, which are known as the noble gases: helium, neon, argon, krypton, xenon, and radon. And the most common forms of oxygen, nitrogen, and sulfur occur as O2, N2, and S8. Continuing, ionic compounds are the gain and loss of electrons between metals and nonmetals, and that if a metal loses an electron, it's known as a cation, and if a metal gains an electron, that's known as an anion. So in covalent bonding, it's known as the sharing of electrons between nonmetals.
Alright, so in the 18th century, a scientist named Lavoisier was able to classify 23 known elements at a time into a group, but just a group of elements lying around. Now, later on came Mendeleev, who classified these elements into what is known as the periodic table, based on some characteristics and the way they are positioned and because of their outer shell. So the periodic table is arranged in a way of groups and periods. Groups is when it goes down, which is vertically, and then periods is when it goes horizontally. Now, what's more important are the groups more than the periods. The groups are arranged based on their outer shell and how many electrons they have in it. For example, potassium only has one element in its outer shell, and that's why it's a group 1 element. So the groups are as follows: as alkali earth metals. This is the transition metals, and they're a bit of a weird, less reactive metals, but they're arranged here, and they have different outer shell balances. So you go from the alkali metals to the more non-metal metalloid group. You have nitrogen, you have oxygen, you got boron right here, you got carbon, nitrogen, oxygen, and then you have the halogens, which are really reactive because they only have seven elements in their outer shell, and they only need one to become what is an inert gas. Now, the periodic table is super important to chemistry because it gives the mass, it gives the outer shell structure, and just by understanding the periodic table, you can understand how almost every element works, apart from maybe some of their quantum relations and stuff. Down here in the periodic table are some artificial elements created, and then obviously the radioactive elements. I think one of the most popular one, uranium. In total, the periodic table is created to just classify elements and group them based on their characteristics, like here's metals, here's nonmetals, here's semi-metals, and just based on their structures. Like in period 2, they have 2 shells, and group 1, they have 1 average electron.
Action.
Okay, so chapter 3 is about stoichiometry of formula equations. Specifically, chapter 3, section 2, determining the formula of an unknown compound. So, for starters, the empirical formula. Empirical formula shows the lowest whole number of each element in a compound, whereas a molecular formula shows the actual number of elements in a compound. So if you look at formaldehyde, CH2O, you can't get any lower than that because both carbon and oxygen only have one element each, whereas hydrogen has two. So acetic acid, lactic acid, erythrose, ribose, and glucose are molecular formulas of formaldehyde. Specifically, acetic acid is a factor of 2, C2H4O2, lactic acid is a factor of 3, and so on. To find the empirical formula, so for example, if we have 2.82 grams of sodium, 4.35 grams of chlorine, 7.3 grams of oxygen, the way you would find it is, so first determine the mass of each compound or component element. So sodium has a molar mass of 22.989 grams per mole, chlorine 35.45, oxygen 15.998 grams per mole. Step 2, convert the mass in grams to amounts in moles and write a preliminary formula. So that is what I've done here. So for sodium, what you have to do is divide the amount you were given by the molar mass. So for sodium, 2.82 grams divided by 22.989 grams per mole will yield 0.12267 moles. And then the same steps for chlorine and oxygen. Step 3, convert the amount in moles mathematically to a whole number subscript. To do that, you have to divide each subscript by the smallest subscript. So the smallest subscript in this case, while sodium and chlorine were very close, sodium is just a few moles smaller. So we have to divide each subscript by the number we received for sodium. So 0.12267 divided by itself will yield 1. 0.12271 divided by the moles for sodium will yield 1 as well, since they're very similar. Oxygen, however, is much larger. 0.46128 divided by 12267 will yield 3.67. Since it's very close, all we have to do is just round up to get 4. So our empirical formula is sodium chloride.
In chapter 4, discusses 3 major classes of chemical reactions. In section 4.3, we have precipitation reactions. Now these reactions occur when 2 soluble ionic compounds form an insoluble product called a precipitate. Thus, the key occurrence here is the formation of an insoluble product through a solution's net removal of ions. You'll see that as we get into this example right here. But first off, in order to identify this precipitation reaction, you have to first use the solubility rules. So we don't have these up there, so I'm gonna have to reference them from my book. But in this example, does a reaction occur when each of these solutions are mixed? So these are both aqueous, which are soluble in water, potassium fluoride and strontium nitrate. The first thing to do is find all the possible net ionic formations between these 2 reactants, which will yield a soluble compound. We use the solubility rules in reference. Now the possible, when we flip-flop these ionic equations, strontium fluoride yields a solid. And we find that because all common fluorides are soluble, but compared with a fluoride from group 2A, which is strontium, it yields a solid. So after you put it into total ionic equation, +2 potassium minus 2 fluoride, strontium +2, and nitrate, we using the solid yield equation, we knock out 2 potassium and 2 ionic. There we go. All right, and the net ionic equation is strontium 2 plus and 2 fluorine minus and SrF2, and that is your precipitate. Now, if a solid does not appear or any insoluble product does not appear in the possible net ionic equations, then no reaction occurs. A solid has to form for a precipitation reaction. Alright, so another major class of a chemical reaction discussed in chapter 4 is the oxidation reduction reaction. In other words, a redox reaction. Now this is where there is movement of electrons between atoms in a formula. We use these to describe oxidation and reduction, which is oxidation is the loss of electrons of an atom within the formula. In other words, the atom is being oxidized or is the reducing agent, thus causing an increase in an oxygen number. The reduction is a gain of electrons, atom is being reduced, or is the oxidizing agent causing a decrease in the oxidation number. Now what oxidation numbers are used to monitor the electron charges of an atoms throughout the formula. Now when finding oxygen numbers of each element, you can determine the two redox agents, reducing and oxidizing agents. So in this example we have silver with nitrate. Oxidation number of any monoatomic ion is 0 with some oxidation rules. A polyatomic has to equal to a charge. So each atom in nitrate has a +5 charge and plus 3 times oxygen has a 2 charge. And so that equals -1. So what times what? Oxygen, so is 2, so that equals -1, perfect. So oxygen is -2 for oxygen. Silver becomes positive, so that's gonna be a +1 oxidation number. And nitrate is gonna be equal to 0, so any monatomic ion has to equal 0, just like that. So nitrogen is +2 and oxygen is -2, so perfect, it works out. Alright, so we see that a silver is gaining, becoming positive, which is, what is it? It is gaining electrons, so it becomes a reduction. So silver is the oxidizing agent. It's being reduced. Is reduced. And a nitrogen right here, you can see a nitrogen becomes +2 in this case. So nitrogen is +5 to +2, so that is a loss of electrons. So nitrogen in the formula is oxidized. Alright, and there you have it. Whatever's being reduced is the oxidizing agent, and whatever's being oxidized is the reducing agent.
Volume of gas can be altered very much by changing the temperature or the applied force. This corresponds to the change of liquids and solids to being much smaller. The characteristics of gas is that they move more freely and have lower density than solids and liquids. Gases also mix in any proportion to form any solution, or to form a solution, which solids and liquids do not. Due to the greater average distance between gas particles than solid and liquid particles, there are differences between their physical states. Gases exert a pressure which is force over area on all surfaces of contact. A barometer can measure atmospheric pressure based on the height of a column of mercury that can be supported by the atmosphere, which is 760 millimeters of mercury at 0 degrees Celsius at sea level. Closed and open-ended manometers are used to measure the pressure of a gas sample. The units of pressure are atmosphere, torr, and millimeters of mercury, and the SI unit of Pascal.
Okay, for 6.2 enthalpy, which is the changes at constant pressure, I'm going to show an example of how volume and pressure can show how it could calculate it to measure the amount of work done. So for example, on this initial state here, we see the amount of volume in this system increases as we go up to the final state, in the final state. So we go from this little bit to this much, and what we want to know what the change of volume is, which is represented by delta V, And it's going to be this little piece right here is the change of volume. So for example, if we start with an initial state of 125 milliliters and we reach a final state of 652 milliliters with an external pressure of 988 torrs, we want to try to find out what is the amount of energy, the amount of work produced. And with these steps, we could do that. First, we need to calculate the change of volume. So obviously, and that is done by using the final volume minus the initial volume, which is 652 minus this number right here, 125, and the number we get is 527 milliliters. But in order to find the amount of work in joules, we need to convert milliliters into liters. And that is just done by one simple equation where 1 liter equals 1,000 milliliters, and you just do the conversion factor and it equals to 0.527 liters. The next step is to convert the pressure from torr to atmospheric pressure. And that is done with the conversion factor of one atmospheric pressure equals 760. And simple mass, we get 1.3 atmospheric pressure. And so now that we have those two volume and pressure, now we can calculate the work it is produced. And that is done with this minus pressure times the change of volume, which is this number times this number, we get negative 0.685 atmospheric per liter. And the final step is converting this into joules, which is 101.3 joules equals 1 atmospheric per liter. So just do cross multiply and we get negative 69.4 joules. Okay, for section 6.3, which is the calorimetry, and is the measuring of heat of a chemical or physical change, we have the equation of Q equals C times mass and the change of temperature. And Q is the quantity of heat absorbed or released by an object. C represents the specific heat capacity, which the quantity of heat required to change the temperature of 1 gram of substance or material by 1 kilogram. And of course, mass of the object, and we have the change of temperature. And this explains that, every single type of metal or element has a certain temperature characteristic that has its heat capacity to be able to be changed. And so for like a little simple example about this is that if you were to heat a piece of iron to 120 degrees Celsius, let's just say this piece of iron is 3 kilograms in mass, and if we dump this piece of iron into a negative 5 degrees Celsius of cold water, with this equation we could figure out how long it will take for that piece of metal to cool down within a certain time.
Okay, so I'm going to talk about the nature of light today, and light is evaluated through the electromagnetic spectrum, and the 4 variables along the electromagnetic spectrum are frequency, which is the amount of complete waves per second, wavelength, which is the distance between any point on the wave, speed, which is the distance per unit time, and then amplitude, which is the height of each crest. And then finally, the particle nature is studied through black body radiation, photoelectric effect, and the atomic spectrum.
Action.
So section 8.2 deals with the quantum mechanical model and the periodic table. So the periodic table is split off into different sections, and which each relate to their own orbital. So the first 2 groups relate to the s orbitals, The nonmetals, groups 3 through 8, are your p orbitals. The transition metals are your d orbitals, and the lanthanides and actinides are your f orbitals. So the way you transition from each element is you have to start off with the 1s, which is the lowest orbital you can be in, starting with hydrogen, moving on to helium. Each block can only contain 2 electrons, each with a different spin. So one has to be positive, one has to be negative, or up or down. This handy chart tells you exactly how you transition from each orbital. So once you fill up the 1s, you have to move on to the 2s. Once you fill the 2s, you have to go to the 2p, then the 3s, and then 3p, 4s, then so on, until you fill up, till you reach the element you want to try to display. So for example, fluorine, which is the 9th element, starting at hydrogen, you start off with 1 electron in the 1s, and moving on to helium, you add another electron in 1s. Then you reach period 2, which is your 2s. You have lithium and beryllium, so you both get 2 electrons in block 2. Fluorine is the 5th element in the p orbital. However, for each block, you have to evenly distribute the electrons initially. So, for example, you would start with 1 electron, then fill up another electron, then another electron, until you have 3. But because it's the 5th element, you have to go back and fill in the previous 2 to get to the 5th. Potassium is just the same way. It's the 19th element, so what you have to do is once again go through 1s, 2s, then 2p, then your 3s, and then 3p and 4s. But because it's the first element in group 4, you only get 1 electron in the 4s block.
Okay, for section 9.1, we are going to talk about atomic properties and chemical bonds. And in this chapter, it starts off with stating that there are 3 ways that elements can form a molecular bond. And the first one we got is a metal with a non-metal. The second example we have is a non-metal with a non-metal. And the third example is a metal with a metal. For the first example, a classic example is sodium chloride, which is salt. And it pretty much is where we have the sodium, an electron transfer of one element to another, causing, which is sodium, giving it to chloride. And doing so, it forms an ionic bond because it's a metal with a non-metal. The second example we have is another example, classic example of water, which is H2O, where we have 2 hydrogens and 1 oxygen, both non-metals, and both are sharing electrons, causing it to be a covalent bond. The third example we have is a metal with a metal, and this is where there's an electronic pulling, and it causes it to be a metallic bond. And this is just briefly because there are d orbitals where electrons are just up for grabs, and they both, gravitate to each other. And the example for this one is copper and tin, which forms bronze. Okay, for this section on 9.2, which is the ionic bond model, I'm going to explain just the classic example on how a metal atom transfers its electrons to a non-metal atom. And for this one, I'm going to use a lithium atom, which is a metal atom, and a fluorine atom, which is a metal. These two form together as ionic bond. And for there are 3 ways to demonstrate this type of transfer of electrons. One is the electron configuration, second is the orbital diagram, and the third is the Lewis dot structure. For the electron configuration, we use the atomic numbers to show where the electrons are and what are the valences available. So lithium has 3 electrons within its atom. So the first orbital is the 1s, and there are 2 electrons in that one. And to make one more 3, we need 1 more electron, which we go down the row is 2s. 2 plus 1 equals 3. And fluorine has 9 electrons in its atomic structure. 2 are in its lower orbital, the 1s, and 7 are in its valence electrons, the outer number. And so we got 2, and then plus 2 is 4, and then 5 is 9. Now, for this example, the electron configuration shows where the electrons go. So once we've written all of them out, we can see that this electron goes to the p orbital in the fluorine. So the fluorine, since it's transverse, the fluorine has a full octet. And we can see that was the orbital diagram, which is different from an electron configuration where it draws out every single electron spin going up and down. And for do so, we need to fill up every level first before we go on to the next level. So the 1s gets filled, 2 electrons. 2s gets filled, 1 electron, 3. Fluorine, the same thing, 1s gets filled first, then the 2s, and then the 2p, which each one gets filled, and then the next ones get paired up before they can be paired up. And doing so, once you put these together, you can see that this lithium atom loses its electron and gives it to fluorine, making its full octet. And for the loose electron, dot symbols depicts the same exact thing, but with the element name on it, with a dot of the valence electron. So lithium only has 1 in its outer electron, because we don't count the inner electrons. Fluorine has 7 electrons around it because we only count the 2s and the 2p, so it has 7. And the same thing for the other two. We see that lithium transfers its electron so that fluorine has a full octet. Action.
This chapter is 2 important topics. The first one is the Vesper theory. The Vesper theory says that to minimize repulsions, each group of valence electrons around a central atom is located as far away as possible from the others. Vesper theory is applied while trying to obtain the molecular shape and to begin the Lewis structure. The next important topic in this chapter is how molecular shape affects molecular polarity. Molecular polarity is created from the effect of the molecular shape, which in turn affects the properties of each molecule. The molecule becomes polar when the bond's polarity reinforce each other. In this case, this polarity is going this way and the other hydrogen is also going this way, so they reinforce each other. That's why H2O is a polar molecule. When the bond molarities do not reinforce each other, they cancel out. That means they're going to be non-polar. The first important topic in this chapter is the valence bond theory and the orbital hybridization. The valence bond theory focuses on how the atomic orbitals of the dissociated atoms combine to give individual chemical bonds when a molecule is formed. This theory rationalizes molecular shapes through the interactions of atomic orbitals during bonding to form hybrid orbitals, right there. In covalent bonds, some of the electrons are shared between the elements, and the VB theory also shows this. It basically means that covalent bonds form when orbitals of 2 atoms overlap and a pair of electrons occupy the overlap region. The other important topic in this chapter is the molecular orbital theory. This theory is basically used to determine molecular structure in which electrons are not assigned to individual bonds between atoms, but are treated as moving under the influence of the nuclei in the whole molecule. This theory predicts the stability of molecular species while explaining the bonding and magnetic properties.